Hello, welcome to m253 Calculus 3 at Cañada College. My name is Lapuz and I'm the instructor for the course. In this video, we will take a look at section 6.5, the divergence and curl, and finally get to see some derivative action on your vector fields. So the div and the curl are two types of derivatives that you can take on the vector fields. But first, before we get into that, let's take a look at the del operator. So we could take a look at the del operator as some sort of mechanism to be able to take the derivative of something. And by derivative, I mean the partial derivatives, because these are the vector fields can be seen as a vector, but each of those components are functions of two or more variables. And so in our study of functions of several variables, we saw that the way to take the derivative of those would be the partial derivatives. One of the big derivatives that we studied back then also was the gradient, and the gradient is actually our first application of the del operator. If we take a look at the del operator as some sort of a vector operation, a vector operator, we can take a look at the gradient as a scalar multiplication of that vector, the del vector. And so imagine the del vector is the partial of taking the partial with respect to x, taking the partial with respect to y, and taking the partial with respect to z. And then if you apply the f function to that, then each of those components in your del operator vector would be the partial of f with respect to x, the partial of f with respect to y, and the partial of f with respect to z. And that's how we found our gradient. So we will think about using this again, but this time our vector fields are actual vectors. Instead of a scalar function f here, we're going to deal with taking the derivative of vector functions. So the div. What is the div? So the div tells us that we're taking the dot product of the operator, the del operator, with our vector field f. So if f is a vector field that's composed of p, q, and r as our functions of several variables, then the dot product of f with the del operator would be taking the partial derivative of the first component p with respect to x, and that's the first component for your del operator, plus taking the partial derivative of our second component with respect to y, and taking the derivative with respect to y is our second component of your del operator, and then taking the derivative of r with respect to z. Notice that the div gives you a scalar function. So you start off with a vector field, which is a vector, and then you take the dot product, and you take the dot product of two vectors, you get a scalar, and here we actually have a scalar function for the div. One way to visualize a div, or try to imagine the geometry of it, is how something expands or contracts as it moves through the vector field. So our example would be an outward vector like x comma y, and as you go out and follow those vectors, it looks like the vector field is expanding. So if you imagine putting a box there, would the box expand as you go further and further out and following the flow lines of your vector fields? And in this case it does expand, and so we would say that this would have a positive divergence. If it kind of shrinks down, we would say it has a negative divergence. But an interesting aspect of something is that if it doesn't shrink or expand, then it has a divergence of 0. So our example is negative y comma x, that vector field that gives some sort of circulation around. All this does is circulates your objects. It doesn't expand or contract it, or doesn't expand or shrink it. And so here it would have a divergence of 0. Although more interesting things are happening here. The next derivative would be the curl. And again, using the del operator on the curl, we can apply the curl as if it was a cross product. So you're taking the cross product of the del operator with the vector field. And the formula for the cross product is actually when cross product was first introduced with regular vectors, we saw a formula, but we said, oh, that's too difficult to remember. So let's find another way to do that. And the way we did that was through a matrix and finding the determinant of the matrix. So you can set up your curl as, again, the determinant of a matrix, where the first row would be the ijk, just as a placeholders, and then the second row would be your del operator as an operation, and then your last row would be the actual vector itself. So if you imagine doing the determinant of this matrix, you'll see that you'll get the curl formula. How does that work geometrically? The curl is how things rotate as you move along the vector field. So that outward looking vector field, again, just pushes things outward. Now it expands things, but it doesn't rotate anything. So this would be an example where the curl looks like it's going to be 0. Now the circulation one, the one where we went around in a circle, we saw that the box all rotated. So we can see the rotation happening here as well. So here the curl will have some sort of rotation. Now the rotation is measured as a vector, because remember the curl gives an output of a vector field. So how does a vector field look like? The curl, you take how something rotates and use your right hand, again the right hand rule, and then you curl it along the way that the vector field is moving, and whichever way your right thumb is pointing will be the new vector that comes out of the curl. So the curl will generate a vector field, and for each of these points you'll have a vector that's represented by your right hand curl. And so if you're curling around in a counterclockwise direction, your curl will be going in this case with just a two-dimensional XY plane, your curl would be going in the positive Z direction. If your rotation is happening in a clockwise direction, your curl will be happening in a negative Z direction. Now in 3 dimensions, your curl could be going in a lot of different directions, because you're not just on a flat plane, and so that's when the 3-dimensional version of a vector field and taking the curl of that will be a lot more interesting and a little bit more difficult to visualize. But if you get the idea, the curl as just your right hand rule thumb in the direction of how something is rotating, then that's how you can kind of visualize it. Another word for the curl, notation for the curl, is sometimes ROT, is sometimes very rarely used nowadays, but it used to be called ROT for rotation. It just doesn't sound as nice as curl. Now the div and the curl have some certain properties to it. And one of the properties, or a couple of properties, is that the curl of a gradient of a function is 0. So this first bullet point is an interesting way to find conservative vector fields. And so we kind of skirted around the idea of figuring out when a vector field is conservative. But now that we know the curl, if we take the curl of a vector field and we get 0, then for sure we know that that vector field was a conservative vector field. And in turn, all those other equivalencies happen, like you can find a potential function, it's path independent, etc., etc. Another definition or another property would be the div of a curl is actually equal to 0. And so you have to be careful about using the div of the curl, because when you say the curl of the div, that idea doesn't make sense, because the div gives a scalar function, and the curl, you can't take the curl of a scalar function, you can only take the curl of a vector field. So there's a bunch of other interesting properties and ways to determine whether something makes sense or doesn't make sense. Kind of like the same way we studied the dot product and the cross product of vectors and scalars. how you can take the cross product of two vectors, but you can't take the cross product of a scalar and a vector, for example. So there are certain things that you can try to extend from the idea of finding vectors and scalars, but now we're dealing with scalar functions and vector fields. And so the div and the curl can be seen as the dot product and the cross product, along with the scalar multiplication here. And so you can see how things might work out or not work out in terms of these combinations. So these properties will become important for us. All right. I think that's it for this section, and good luck.